what is MS going to be? 1. And sorry, S is 1. And then what is MS going to be? -1, 0 and 1. So if I did take this and this and put them in the dot diagram, how many possible combinations are there? 9 possible combinations. I can have -1, -1, -1, 0, -1, 1, all 0. So where would that fit into the dot diagram? There will be one dot here, one dot here, one dot here, one here, one here, one here. In fact, if I gave you this alone, what would that mean? That means it's a triplet P state. So if I gave you a 9-component dot diagram, and it's a system like this, then I know I'm talking about a triplet state. If I gave you this, what does that mean? It's triplet P plus singlet S. If I gave you this, what does that mean? It means it's a triplet P, singlet D. What's that? That's exactly this. So what I essentially done is I came up to a point here, and then instead of letting you stare at it and see, please tell me what's sitting inside. We just worked the problem backwards. We took the triplet P state, we took the singlet D state, we took the singlet S state, and converted these into components and put them into a dot diagram, and saw what dot diagram we should be getting. This is what we should be getting. And this dot diagram essentially means I am really looking at a triplet P state, a singlet D state, and a singlet S state. But that's what I got with the big mess that we wrote a little while ago. So you can see the whole problem got sort of broken down into a lot of simpler things. First one, of course, was tedious. You have to look at all 36 possibilities and write out all the components. You summarize those components into a diagram such as this. Then you look at this diagram and see whether you can unravel information regarding these states. If you can't, of course, this is cheating, because I sort of gave you those states and then asked you what these are. And then you look at this and say, oh my god, this is the same. And therefore, it must be triplet P, singlet D, singlet S. But you can look at the state and draw inference from here. The fact that I have only one thing out here, -2, and nothing else over here, tells me that this must be somebody with spin 0, but 1, 2, 3, 4, 5, therefore it must be a singlet D. Once I know it is a singlet D, you remove that and see what is left behind. And you will be left behind with 9 dots over there, with 1 in the middle. But the 9 dots immediately tell you that it is a triplet P. And therefore you remove that, and what is left behind is 1 dot in the center, which tells you that it must be a singlet S. So basically what you have done is you have taken the P2 configuration for equivalent electrons, which essentially gives you 36 possible combinations. You wrote all 36 combinations. You threw away those that Pauli principle will not allow you to keep. And which were the ones it was not allowing you to keep? The ones in which all the quantum numbers are the same, and also the ones which cannot be overcounted. If you've already seen that before, don't count it again. Just switching labels is not going to be a new configuration. You throw that away, because electrons are indistinguishable particles. And that's the reason why you must throw them. And then you throw them away. This basically is what you get.
Triplet D, then all of these were peaceful, right?
Yeah, if I had triplet D, yes, you'll be everywhere.
So, how can I really infer from this that, like, right now we said it's a P2 configuration. So, just looking at the table, how can I say that it's a P2? Because if it's triplet D, then...
No, I start from P2. I know my configuration is P2. I always start with my configuration, and for that configuration, I try to figure out what my states are. So, I start from P2. In fact, what I would like you to do as a sort of an exercise is that you remember the states that we wrote, 36 states, write all 36, we didn't write the last 5, write all 36. Take the ones that we threw away. Okay, take the ones that we threw away, write a dot diagram for that, the ones that we threw away, and see what that really corresponds to. So find out from that table, the ones that we threw away, put that into a dot diagram, and then come back and tell me what are the states that really are the ones that we threw away. Well, the answer is we threw away a triplet D, we we threw away a singlet P and we threw away a triplet S. Because for equal, non-equivalent electrons, we had all the possibilities, right? Triplet P, singlet, triplet D, triplet P and triplet S, and singlet P, singlet D, singlet S. But we threw away some of them. Which ones did we throw away? We threw away triplet D, we threw away triplet P, singlet P, and we threw away triplet S. So what you should now do is confirm from this diagram, take the ones you didn't keep, the ones you got cross, put them into a dot diagram and see if that really corresponds to triplet D, singlet P and triplet S. It must be. And then you know that out of the 36 combinations, only 15 were really allowed, which gave me the 3 states. And the other 21 states, or 21 configurations, or micro states as it is called, we threw them out because they were wholly disallowed. And that's the way you really have to work out the electronic term symbols, or the term symbols for atoms with equivalent electrons. It's not easy, it's very tedious. It's not difficult, it's just tedious. So you can imagine how it would be for a D2 configuration and an F2 configuration and so on. You will just have to write all these, but then you don't have to, because today you will find that for whatever configuration you need to, these states are already there. And there's also a certain pattern that you must be able to see. We saw that this was singlet S, triplet P, this was P2. If I ask you for D2, what happens? You just progress further. It will be a SPDF, you will get that. And if you can just keep going to the next orbit, you will see that this progresses. Of course, I gave you P3 configuration or D4 configuration. It gets very messy because you got to take 2 at a time and add them and then go on. And it will be really messy. But you don't have to do it because all these have been done and you can basically refer to these tables of microstates and term symbols. So this is basically what we did. From tomorrow what we will do on Wednesday, we start looking at term states for molecules. And we look at electronic spectroscopy of molecules as opposed to what we did for atoms, and we will take it from there. I will schedule these over